Hi friends, today I have a new video on Gram-Schmidt Orthogonalization process and Orthonormalization and the Numerical Linear Algebra. Let's get started. I'll be speaking on orthogonalization versus orthonormalization as far as numerical linear algebra is concerned, and then we'll look at some applications of Gram-Schmidt process. When you talk of orthogonalization, it's basically a process of constructing a set of orthogonal vectors that span a particular subspace. And we say suppose we have a set of linearly independent set of vectors v1, v2 to vn belonging to v in the inner product space. We can construct a set of orthogonal basis vectors u1, u2, un from the inner product space or the included space that will be of the same subspace such that the new set of vectors and the old set of vectors must have the same linear span. And every other vector in the new set is orthogonal to every other vector in the new set. And then orthonormalization, on the other hand, is a form of orthogonalization in which each resulting vector is a unit vector. So suppose u1, u2, un is as orthogonal basis, then we can have our u1, our w1 to be u1 over the length of u1, and then w2 to be equal to u2 over the length of u2, and then we continue that one to it happens to get our wn, of which our w1, w2 to wn be the orthonormal basis. So here are some of the orthogonalization algorithms, and in this video we'll be looking at the Gram-Schmidt process, and then in the subsequent videos we'll look at the Hausfelder transformation and the Givens rotation. And then there is a theorem of which we need to consider. They say any orthogonal set is linearly independent, meaning one is known as scalar multiple of the other. Okay, of which from few examples we justify this theorem from few examples. So we want to look at the Gram-Schmidt process in general. So given that we have under many vectors, we'll look at Gram-Schmidt process in general under many vectors. So considering as vector space V in an inner product space of which you have our v1, v2, vn to be a basis for V, then we assign our v1 to start this orthogonalization. We first of all assign our v1 to our u1, and then to get a u2, we have our v2 minus the projection of v2 onto u1, and then we have our v3 to be equal to v3, u3 to be equal to v3 minus the projection of v3 onto u1 minus the projection of v3 onto u2. So the projection that we have here, we consider this one as the inner product of u2 comma v3 over the inner product of u2 comma u2. Okay, that means our u2 that we have here, that's what we consider to be the projection of v3 onto u2. Okay, and it continues that way until we get our un. So let's look at the first example on the Gram-Schmidt process. So the example 1 says we'll apply the Gram-Schmidt orthogonalization process to the sequence of vectors in R3 and hence find the orthonormal basis. So this is our v1 vector, which is 1, 1, 1, v2 vector 1, 2, 1, 2, 0, and v3 vectors 2, 0, 1. Like we have seen from the algorithm, first of all, we assign our v1 to our v1 to u1. So meaning our u1 is now going to take what the v1 vector. And then to get a u2, we'll look at a projection of v2 onto u1, which is our v2 vector to be equal to this. And then the projection vector is the whole of this. So when you subtract, then we'll be getting what? Our u2 vector 0, 1, negative 1. And then to get our u3 vector, we have what v3 minus the projection of v3 onto u1 minus the projection of v3 onto u2. And then we have our v3 vector over here, and the projection vector is the whole of this one here. And then our projection of v3 onto u2 is going to give us the whole of this. So after doing our simplification, we will then be getting this vector 1, negative 0.5, negative 0.5. So when you consider this vector, our u1 vector here and this vector here, our u2 vector here, when you find the dot product of it, it is going to give us what? 0. And then we can also consider this vector here, u2 vector here, and u3 vector here. If you find the inner product of it too, it is also going to give us what? 0. This one shows us, shows us that our each pair of vectors each pair of vectors in the orthogonal basis is going to give orthogonal basis is going to result to what? 0. Then we go ahead to find the orthonormal basis. So then we have this to get our vector v here, u1 here. We'll find the norm of it. When you find the norm of it, we are going to get what? Norm of it, we are going to get root 3. So 1 over root 3 is going to times our vector u1 here is going to give us this. And then find the length of this vector, which is root 2. And 1 over root 2 times the vector u2 will eventually give us this vector that we have here. And then to get a w3, we still find the length of this very vector that we have here. We find the length of it, and the length of it, 1 over the length times the vector here will eventually give us this vector that we have nicely here. So all these vectors that we have here are orthonormal basis. Orthonormal basis. The unit length of these vectors are 1, 1, 1. And then we have example 2 here, which says what? Which says given that a vector v is a subspace of R4 with bases that we have here 1, 0, 1, 1 and 0, 1, 1, 1. Find the orthogonal basis and their respective orthonormal basis. So like we have done in the previous one, we first assign u1 to be equal to v1 to be equal to u1, and then we'll look at the projection of v2 onto u1, which eventually gave us this vector that's negative 2 on 3, 0, 1 on 3, and then 1 on 3. Then we quickly find the length of this vector here, which is what? Square root of 3, 1 over square root of 3 times the vector here gives us this vector that we have here. And then we also find the length of this vector here, which when you divide it by 1, we'll be getting this root 6 on 3, and the root 6 on 3 times the vector here will eventually give us what? This orthonormal vector. So click the like button and hit the subscribe button. Thank you. And keep subscribing, keep commenting. If it's something that you love so much about the video, please leave your comment down below. Thank you.